So, welcome back to this tutorial of CFD. So, in the previous session, we had checked upon meshing and rest of its properties, types, and also the metrics. And then we had checked on inflation layer, which is required near the boundary layers. So, now we'll be jumping on to numerical discretization. So, I'll just write it down. Uh, So numerical discretization technically, as we have discussed before, is just trying to simplify your equations into solvable format. So numerical discretization. Okay. So for this, so what does this mean? So you have, so now we have checked on conservational laws, right? Conservation laws. So in these laws, when you had applied like when you had substituted values for the parameters phi, that is either phi can be your 1 or v or I or species C, etc., you get different equations, right? When you replace all this into the transport equation, correct? Transport equation. Now, for example, let's take the Navier-Stokes equation that, or the momentum equation that we had checked, right? So what was that? So that was your dou uh, rho v by dt plus del times rho v is equals to your del times u v u plus s times of so it's u, right? So u source of u. So this is again, as we had checked before, this is the diffusion term and this is the source term, right? So this equation, you can see that all contain gradients and partial differential your partial differential equation. This whole thing is a PD, right? So now in order to solve this, your solver doesn't um, solve a PD directly. What it does is it discretize it into smaller or easier equations, simpler equations. And how is that done? That is done using discretization. That is this topic that we are going to cover up now. So you have methods, many methods of discretization. We are not going much deep into discretization, but I'll just tell like a general idea of how it's done. So moving on. So the first thing that we had checked on was your Taylor series, right? Taylor series. So you can write as fx plus delta x is equals to f of x plus del x df by dx plus del x the whole square d2f by dx square, and here you'll have a 2 factorial, so plus 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 plus, so you can have del x to the power n dnf by dxn, and here whole divided by n factorial, correct? So now what we would be needing in equation is, suppose this, or depends if you are going into a, if it's a second order derivative, then you will be needing this value, right? So how this works is, so you ignore rest of the terms, so till here, so rest of the terms after this, so you consider this equation, right? And then after substitution, so you can find either the value of this or this, depending on what you need in the equation, right? And you'll get it as a in the terms of the function's value itself. So here you are directly finding df by dx value. So here if I substitute, if I'm only taking finding df by dx value, I can write it as your f x plus delta x minus f of x divided by del x, right? So this is one form of discretization using Taylor series. Now if you want d2f by dx square, again, so you take this whole thing, substitute this side, so f of x plus del x minus fx minus del x into df by dx divided by your um, de, uh, which term? Del x square and multiplied by 2 factorial. And then you can write this df by dx in terms of this term. So you will get a big equation. But again, since all of them come are in terms of the function's value itself, it's easily solvable by the solver, right? So you don't have to do any calculus in order to find those values for the partial differential equation. So that technically is what the idea of your discretization is. So in general, if I just say, so you have your PDEs, so you convert PDEs, convert into solvable, simpler mathematical equations, right? That are usually in the terms of the values of the function itself. Function itself, right? So this makes sense. So you have a PD, it gets converted into a solvable, simpler mathematical equation, and it's written in the terms of the values of the function itself. So as you have seen up, so yeah. So this was your PDE, and we converted this PDE into a simpler equation. You found the value of this derivative using a Taylor series here. So here is the value that you find out, and these are all in terms of the values of the function itself. So it is easier to solve all the uh, equations, or all the conservation equations that are enforced into each control volumes, right? So what I mean is, now suppose I have this body, I have divided into control volumes. I'm enforcing each um, into each cell. I'm enforcing, suppose, the momentum equation. Now while solving the momentum equation for the values of gradients, that is, so in momentum equation you have d rho by dt, right? D rho by dt, and then you have plus your grad terms, so gradient terms. So all these values are computed using your discretizations, and these values are uh, converted into, I mean, these functions are converted into uh, in terms of values of the function itself, right? So here you get it into simpler terms, and then you can solve the equations faster and easier, faster and easier. So instead of solving the PDE, you are directly converting it into a simpler form and solving it, right? So you're, in short, you can say that you're trying to avoid calculus and going the numerical way. So that is your numerical discretization. So now here you have seen before. I'll just touch upon those again. So you have seen few methods as last time I had mentioned. That is your forward difference, forward difference, your backward difference, backward difference, and your third one, that is your central difference, right? So all these are technically derived from the Taylor series itself when you substitute values. So here you can say df by dx is equals to your f I plus 1 minus fi divided by del x, right? Then here you have f of I minus f of I minus 1 divided by del x. So simple to understand, forward difference. So you're taking one term ahead of I. So I is where you are right now, the iteration that is going on. So you take a forward iteration value minus the iter you are running on divided by the step step value. And here again same, here is backward difference. So the current position you are at, the current iter you are at, minus the previous iter divided by the step value. And in central difference, it's just you take one ahead, so fi plus 1 minus 1 below, that is fi minus 1. But now since the step is 2, you take 2 delta x. So hopefully this is understood. So I have I plus 1, and I have I minus 1 iter. So these are my iters or iterations, right? So the value of f is what I'm finding. So f of I. So when you're going for forward difference, you take this into consideration. Backward difference, you take this into consideration. So I'll just write f, that is forward, backward, and for central, you consider this whole thing. So that's why you have your 2 delta x as your step, because this is one step, this is another step, and this is your central difference, right? So this is again, these are methods to discretize equations. So you can directly use wherever you find df by dx, you can just put these values and just resolve it easier. So hopefully that's understood. Now we'll move on to one of the most important concepts in CFD, and that is your upwind concept. Upwind concept. Okay. So what is the upwind concept? So okay, let's assume that you have a phase, I mean you have a point P and you have a point E, right? And there's a phase between them. So this is, suppose this is your cell, right? And it keeps going on, okay? It's just continuous cell. I'll just take this as W and some center Q. Now I want to know the value of the parameter, that is phi, at this phase. Okay, so I'll just change the color. So suppose I want to find the value at this phase. So how will I find? Because as I said earlier, what was FEM technically? Your FEM is finding flux. And how do you find flux? So if I have two elements, the flux would be on the phase, right? So suppose there's something moving from here to here. So the flux would be in, that is this side, minus this, that is out. That will be a net flux. So one important point to remember is flux is calculated across the phase. So in CFD, what we always usually calculate through is the phase value of the parameter. So what does the upwind concept say? Well, it's pretty simple. So you know what upwind is, right? So it's like, assume you have, I mean, there's industry here and it's releasing some smoke, okay, and it's moving this side, fine. So if I just take like a zoomed in view, right, your smoke is traveling in this direction, correct? So now assume that I have divided into cells. So what upwind says is that if I have to find the value at this phase, take the value of the previous center. Okay, why? Because it is coming from, suppose here the flow is coming from the previous center, right? So the upwind concept says take the value from the previous cell center. So suppose this I'm denoting as small e, this phase is small e. So what the upwind concept says is your phi e, that is the parameter value at the phase small e, is equals to the parameter value at capital P. Okay, does that make sense? I'll just draw the diagram again here. So you have two cells, right? Hmm. Yeah, that's perfect. So you have P, you have E, and these are cell centers, and this is phase E small e. You have to find, and here, so you have parameter P, and here it's parameter E. So if you have to find parameter small e, it is equals to the parameter capital P. That means the value of the parameter at the phase is equals to the value of the parameter at the previous cell center, right? So this is the previous cell of this phase, that is P. So your parameter value at at E will be equals to parameter value of E. Again, so as I told, since you are assuming that the flow is coming from, so the flow is going in this direction. So if the flow is going from here to here, you are saying that um, whatever value of the parameter is at here is continued to the phase, and then it changes at the next cell center, right? So you are not assuming any contribution from the E. So that is what is the upwind concept. Now there are few things that you must know about this. So you have two kinds of upwind concept. There are two types. So one, let's write types. One is your first order, and the second one is second order. So first order upwind and second order upwind. So what does these mean? Your first order is just technically what we just discussed. That is your phi at the phase equals to the just the value of the parameter at the previous phase, p, right? And okay, just to avoid any confusion, phi here can be any parameter: pressure, velocity, rho density, energy, etc. So if I want to find the pressure at this phase E, small e, then it is equals to the pressure at the previous cell center. Small p is what the first order upwind says. Now there's one thing that is um, a discrepancy in the first order. So let's say I'll just take an example. So for the first order, when you are looking to the first order upwind concept, so now let's say that you have a cell, suppose it's 0 0 0 1 1 1 1. Okay, this is your centers. So just assume 1 is the value. Okay, so and the vertical lines are the faces. So just assume this as one of the configurations. So whereas here you have zero pressure and here you have the pressure is 1. Okay, so the value for finding the parameter value at the next iteration, I'll just write the formula for that, is your phi of n, that is the first iter, minus the c times of phi I at n minus phi I plus 1 times n, right? So this is the formula that we use to find the value of the parameter that we need for the next iter. So let's say for iter 0 you have iter 0. Okay, that's the 0th iteration. So you have it 0 0 0 1 1 1 1. Now let's say your c value, that is, so just before we get into it, I'll just tell what c is. So your c is your um, CFL value. CFL value. Now what is CFL? CFL is your current Friedrich Louis number. So what does this CFL mean? So CFL, actually we will be covering it later up, but I'll just tell here what it means. So CFL tells you how much of information passes through um, at one time step or one mesh element, right? So the formula is your V delta T divided by delta X. So it's simple. So this is the information passing through, information passing, and this is your the mesh element, right? So what it says is how much information is passing through a mesh element, or in simple terms you can say that how many cells does it skip in order to get one information passed through. Okay, so CFL is required in order to know how far information travels in one step. So if CFL is too large, so if your CFL is too large, what will happen is that info jumps over many cells, right? So many cells, and uh, if CFL is low, which is what we prefer usually. It means that information, I'll just go down. It means that information is moving, or I'll say not moving, jumps less over cells, right? So now why is this CFL important? Well, you will see it uh, when I cover explicit and implicit solvers. But for now, just assume that CFL, or just know that CFL is how far information travels in one time step, right? So this is one time step in how much information passes through that at one time step. So hopefully that's understood. So CFL value, let's just assume it to be around 0.5, right? So what does it mean? So 0.5, half of the information travels to uh, the whole system per time step. So per time step, it covers half a mesh is what in short it gives an idea of. So now, okay, you got the values of that. I'll just go up. I'll just keep it on side. Yeah. So we'll just cover this up here. Okay. So at the iter 0, again, so it was iter 0. It was just 0, 0, 0, 1, 1, 1, 1. Now we are going to iter 1. Iter 1. So here, now how can I write this equation as? So here it will be your, for this term, I can write it as this term. I can write it as 0.5 times of 0 plus 0.5 times of 0. So 0.5 is your CFL and 0, 0 are the values of the iters, right? Of these iters. So what happens is here you get 0, this is fine. But when you are going into this time step, right? So here what will it be? Here you can say it's 0.5 times 0. So that's the previous cell value plus zero point 0.5 times of 1, right? So this will be equals to 0.5. So this is this value that I calculated. Now the present iteration, the present cell value is 1. So the net value of that cell will be equals to 1 minus 0.5, that is equals to 0.5, right? So now you can see in the first iteration, this has become 0.5. The value of this has become 0.5. Now this will remain 1, this will remain 1, this will remain 1. Now as iterations go, each of the value gets decreased. So what does this mean? Now let's say after I run more iterations, suppose I have reached iteration iter 100. I can say the values might have become suppose 0, 0, 0, 0 point, I don't know, like 0.062, 0.312, 0.68, and 0.93. Okay, and how was it earlier? It was 0, 0, 0, 1, 1, 1, 1, right? Correct? So initial, for iter 0, iter 0, it was these values. And then iter 100, it has become these values. So what did you see? You have seen that the value of the pressures, or whatever, the parameter has diffused into each other. So the value has now reduced, right? So this reduction is what we call numerical diffusion. Numeric, numerical diffusion. Now what's the what problem, you might ask? Well, now if I would consider this to be the pressure, like 0, 0, 1, 1, 1, 1. So what does this mean? That the pressure was 0 and there's a sudden increase of pressure into 1, 1, 1, 1, 1, right? So there, this might be a case of shock wave, right? So a sudden increase of pressure, usually, what does it mean? So you can say that it might be a sudden change in pressure might indicate that it's a shock wave. Now, but when you reached iter 100, what happened was you saw that the values submerged, so it's 0.602, and now there's not much difference between 0 and 0.062, right? So I mean 0.000 and 0.062 is just a 0.062 difference. So you can say that now the condition, you cannot say that it might be a shock wave, right? Because it's submerged now. The value that was 1 initially, and so 0. So you could see a contrast. You could see a sharp difference, or increase in pressure. But here now you can't see that difference. So this just submerges the case of a shock wave, and that is not what we want, because we want our model to capture, or our solver to capture all details possible. So if there's a shock wave, the um, the solver should capture what do you say, the shock wave. But then here, as you saw, it just submerges the value, because of which you get a gradient like this, as I said. So 0.062, 0.312. So here now the details are not captured at higher accuracy, right? So here the whole idea of shock wave just goes apart, because you don't see a sudden increase in pressure at all. It's just a gradual increase, and that can happen in any normal situation, right? So that is why that is one of the disadvantages of your first order upwind. That is, you have numerical diffusion where your values get submerged or diffused or reduced as you go ahead in iterations. That is, there's a gradual shift in the values, which submerges cases like shock wave, where there is sudden increase or change in the value of parameters like velocity and pressure, right? So yes, so that is numerical diffusion, which is a disadvantage of the uh, upwind concept. So just in case anyone didn't understand, I'll just rewrite the formula. I n plus 1 is to phi n minus c times of phi I n minus phi n sorry, n and I minus 1, right? So what does this say? So as we saw, so this is the new value of the parameter phi, and so again this means that you're uh, checking. So this is the next value. So there is the phi new is equals to phi old minus c times your, again, phi old minus I minus 1. That is the phi old of the previous cell. So in case you didn't understand this equation, you can just remember it in these terms. So just for easier understanding, I'll just um, let's just draw one diagram. So you have cells, right? And I'll just draw two more. Yeah, so that should do it. Okay, I'll just draw one more. So now let's just name them. That is P, Q, R, S, T, U. So suppose I'm finding uh, the phi value for R, right? And iteration 0, you know the value at iteration 0. Suppose it was 1, sorry, it was 0, 0, 1, 1, 1, 1. Okay, these were the first values of the parameter phi. Okay, and these are the cells. So now if I want the value of phi at the new point, so phi r new, that is the next iteration. So I'll go at iter 1 new, or I can say iter 1 is equals to, I'll just remove this. So at iter 1 is equals to your phi of r, the old or the current cell you are in, that is iter 0 minus c times, that is your CFL number times brackets. Okay, let's erase that. Huh. So your CFL number times CFL number times your phi of r old minus your phi, I'm sorry, not minus, it's plus your phi times the previous cell, that is q old. Fine. So hopefully that makes sense now. That is how we got the values for each of the iteration. So assume this was 1, your CFL was 0.5, so your phi at r new would be equals to your old value, that is 1, minus c is 0.5 times r old is your 1, and plus your q old is 0. So this is 1 minus 0.5 and this equals to 0.5. So this is how your value of the new parameter plus the new parameter in each of the iterations is found. And I'll just correct the equations here. It's plus, right? So yeah, so this is how you calculate the value of phi across each iteration for a given cell and for a given parameter uh, in the upwind concept. So as you saw, this is the problem that we discussed, that is numerical diffusion. Numerical diffusion. So just for an easier intuition, you can just think of like when there's I don't know, you have a ball of water and then you put suppose a blue ink, and when it drops, it starts diffusing into its uh, other neighbors, right? So that is what is happening here. So you had sharp differences between each, that is your 0 and 1. You had a sharp difference in the parameter value or pressure, you can say over here. And but once the iteration keeps going on, your values submerge and decrease and it gets transferred on, because of which it then you know submerges the value, because of which then you don't significantly see that increase in uh, or the sharp increase in value, so which then submerges the whole point of the conditions like shock wave or any other conditions, right? So that's why numerical diffusion is very important to understand, and no textbooks have this clearly written. So yeah, hopefully it's understood. Now, in order to tackle this, the second order, okay, the second order was introduced. So second order upwind, second order upwind condition. So in this, what they do is simple. So you can say that your phi e, or that is your parameter value at the phase small e, equals to your previous cell center value, that is p, plus your del times of phi into distance, right? So what does this say? So what is this term? This is your grad term, so gradient, right? So how is it helpful? So here what you see now is that along with the previous phase term, it is previous cell center term value, it is also adding a gradient which fixes for the submersion that was caused here. So here you see that there was a decrease in the value, right? So now what happens is, now there's a plus grad term that comes up, and this grad term compensates for the loss that had happened during the uh, first order upwind concept, right? So in first order concept, I said that the value was getting transferred, right? So it just, the value keeps going on like this as each iteration goes. So they're like q, p, r, st. So the values of each phase just keep diffusing into the other phases, because of which you see reduction in values of that phase. So that was causing the numerical diffusion. Now here, this is compensated by the grad term, the gradient term. So now what is this? So this term is the change in phi. So it says how much phi has changed. Now this is with respect to distance, right? So you just multiply that into the distance between the cell and the cell center and the face. So if I have this, right? So this was P center, this was E, capital E center, and this was face E, small e. So phi E would be a phi P, that is the value of the parameter at the center, and I'll assume this is at a D from the face. So now I have plus your gradient of phi, that is how much um, your phi changes with respect to D distance into the distance D, right? So this should compensate. So it tells how much it. So you're taking this term, that is grad phi, that is how much. So it's like an approximation of how much phi would change as you go ahead in distance. It's an approximation, of course, into D, that is the distance that is between the cell center, the previous cell center, and the face. So this compensates for the loss that was caused during the uh, first order upwind concept, where you had numerical diffusion, right? So this prevents prevents numerical diffusion, right? So this is what is the second order. So this is much more accurate, but it's less stable. So your first order upwind was more stable, because you're just considering the previous values, that is, a phi p was equals to phi e. I'm sorry, that's the inverse. Your phi e was equals to phi p. So it was just a normal, simpler, faster calculation. So here, there can be cases of divergence, because you are using an approximation of grad phi into D, right? So there's possible that this solver is less stable than the first order condition, because first order is just a simple assumption saying that your value of the current phase is equals to the value of the parameter at the previous cell center. So because it was simple, it is more likely to converge, and it's like, you can't say it's easier to converge, you can just say it's more stable, because there's not much of any calculation. So here you have to, for calculation of this term, that is grad phi d, this term makes the solver a bit uh, less stable than the first order upwind concept, right? So now we have checked on both, that is the upwind concept, the first order upwind and the second order upwind. Now let's just see the solvers that um, usually you see. So you checked your first order and second order. Now we have three more methods. So I'll just go in them in brief. So now we'll just go on to the other methods. So one is, the next one that we are gonna check is MUSL. Sorry, quick. So it is your third one that we're gonna see. QUICK. Quick. So what does this indicate? It's just an acronym. So it's quadratic upstream interpolation for convective kinematics. Convective kinematics, right? So again, as I said, usually it's just the upwind and the first order upwind and the second order upwind conditions, methods. Now these are just built upon each of them for more accuracy. So we'll just take brief looks on it. Won't go much in details. So the quick method just uses 3 points. It uses 3 points for calculations. So here in the second order, sorry, the first order, how was it working? It was working just based on 2 points, right? So this value and the previous value, as I said, the phi n I is equals to your uh, phi, okay, for the n plus 1 iter is equals to your phi n I n minus c times phi I n plus phi I plus 1, sorry, I minus 1 n, right? So you had your previous cell and the current cell. So that's why you had only 2 cells into considerations. In quick, you take 3 points and then you run it on a quadratic interpolation. So this is more accurate than rest because of course you're taking 3 points into consideration and then you're using a quadratic interpolation. So it is much more uh, accurate than the first order and second order because they were just running on basic assumptions. And so this is very accurate. Low diffusion, right? So but here you have oscillations possible. So I won't go much in detail about this, but just in brief, if you can understand, in numerical diffusion, you knew that the value is it's going down, right, like this. So what happens in oscillation is just another opposite. So it's numeric dispersion. So now your values just keep going up, down, up, down, up, down. Uh, that is possible in this quick method, is what we are saying. So yeah, that is the quick method. Going into your MUSCL method. So going on with MUSL, just select the pen. So yeah, your fourth method, that is MUSCL. Won't call it a muscle because there's no E. But yeah, so this is now monotonic upstream centered scheme for conservation loss. Okay, I feel the full forms are made based on the short forms. This genuinely doesn't look like some full form that they intended to make. But yeah, moving on. So this is usually used for compressible flows. So what MUSCL does is it uses neighboring slopes, right? Neighboring slopes. So what does this mean? Just in short, I'll just explain what it would mean. So in the second order upwind concept, you saw that it was phi E is equals to phi P plus your grad phi D, right? So now grad phi was calculated based on these 2 points, right? Now this phi is sorry, this grad phi, that is the slope, is found using the neighboring points as well. So if this was my cell E and I have P, I have Q, I have R, and I have S, right? So now the slopes, the grad phi term is calculated for all the possible configurations, that is all the neighbors, right? So you'll have 4 grad phis for this configuration thing. Now you can have more as well if I consider neighbors over here, 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 and here. But yeah, so you consider more slopes, so you get a better understanding of how your parameter changes. So your grad phi value is considered using all the neighboring elements, and then you multiply into the distance remains the same, that is from this to this, and now that is how you calculate the value of the new value of parameter using MUSCL. So it's so just in short, if I mention how quick works is in quick you use 3 points and you use a quadratic interpolation. In MUSCL you use um, multiple slopes of the so you use the slopes of the neighboring cells and then you uh, combine it to get the value of the new parameter, right? So this was the fourth one, and now the last one is your TVD. TVD. So this is TVD. This is total variation variation diminishing diminishing. So you don't need to know all these in detail at all. Only the first order and second order upwind concepts were the most important ones. Rest are just additions to that same concept. So here you just, as I told, there was um, numerical dispersion and uh, oscillations possible in the quick method, right? So what I mean the quick and the second order upwind method. So what the goal is to reduce those oscillations, reduce oscillations between values. So here the condition is that the total variation should never increase, should never increase. So this just logically makes sense. So if you put a cap on how much variation is total variation is allowed, you can't allow the values to jump over a point, right? So it just keeps reducing uh, this upper jumps oscillations and just converges into one single line of solutions, right? So that is what your TVD does. That is, your total variation is shouldn't increase at all. So you cap on the total variation and you go on calculating the values. So this reduces oscillation between values. So yeah, so this was the upwind concepts, or this is how you would calculate the phase values, right? So all these things that we did right now, so the 5 methods that we used, so from your main is your upwind concept, upwind. So in upwind you had FOU first order upwind and SOU second order upwind. Then you had quick. Then you had MUSCL. Then you had TVD. So all these methods are used to calculate what? It's used to calculate the phase values, right? As I said. So all these concepts were applied in order to get the phase values. So this is P, this is E. You needed E. That is the phase E value. And why we needed this? Why? Well, simple. It's because you're calculating flux, and flux is always through the phase, right? So if you have 2 rooms, suppose, right? And if you want to know how much went in and out, so in and out, you would have to look through the door, right? So it depends. So if there's a door and there's 2 rooms, okay? So I'm passing air from this room to this. So room number 1 to room number 2. It depends on how much I open the door, right? So if I bring this analogy, so your door is your face. So your phase is what controls the flux, and hence we need only phase values during CFD or any such analysis, right? So that is why we need all these concepts. So these methods, that is your upwind concept, your quick, MUSCL and TVD, they are used to calculate the phase values, right? And phase values are what? So this can be any parameter, face value of the parameter. Now that can be a pressure, velocity, density, energy, etc. Right? So this was all about your face values and your concepts related to that and how you would calculate phase values. So next that we would be touching on is your pressure velocity coupling. So that is another important topic. So you'll have now another set of solvers for that. So we'll be discussing that in the next part. Thank you.